All right, here we go. Unit for day one. Today we are going to be talking about implicit differentiation. So by the end of today, you are going to be able to take the derivative of functions that are implicitly defined. So what implicitly defined means is instead of having a function where y is explicitly, meaning spelled out exactly, defined in terms of x, you're going to just be given a general relationship. And so an example of this would be a circle. We cannot write an equation that describes a circle that is solved for y. The reason is it's not a function, right? We have multiple x values for single y values. So this is an example of a case where you might need an implicit equation. And we have such an implicit equation. X squared plus y squared equals 25. Every point around that circle is a point where the x coordinate squared plus the y coordinate squared would give us 25. And just like with a normal function, we might have questions that we'd want answered. We might want to be able to look at this point right here and know what is the slope of this tangent line. What is the slope of this tangent line, aka what is the derivative of y with respect to x? So we might still want that even though we don't have a function defined in terms of y. And so what we're going to do is this is a technique called implicit differentiation, and it is basically just an application of the chain rule, but it can be a little tricky to see the first time. What we're going to do is we are going to take the derivative with respect to x of both sides. So this means take the derivative of x squared plus y squared with respect to x, meaning how fast is x squared plus y squared changing with a very tiny change in x. And just like in Algebra 1, just like in Algebra 2, just like in third grade, as long as you do the same thing to both sides of an equation, that's a totally valid operation. We'll do the easy part first. 25 is a constant, so it's not changing at all with respect to x. And on the right, we're going to have on the left, we're going to have a little bit more to talk about. So let's break this up. This is a derivative rule. If you are adding two portions inside a derivative, you can take their derivatives separately and add them up. The first one's going to be easy. The second one's going to be what's new for today. The first one, the derivative of x squared with respect to x. So all that is asking is how fast is the x squared function changing with respect to x? And we know that through the power rule, the derivative of this function is just 2x. But where things get tricky is when we go to this next statement, you may be thinking that we can just say, oh, this is 2y, but it's not. That would be the derivative with respect to y of y squared. You can only do that if you're actually finding the rate of change of the same variable. So we can't do that. But what we can do is we can say that we are taking the derivative of some function y, which is defined in terms of x. Because there is some relationship that exists between y and x, we just haven't solved for it yet. But what you need to focus on here is that this is a function x inside another function y. So this requires the chain rule. And so if we go to take, and I should more accurately write here because this is what's actually going on, I should write that this is squared. When you take the derivative of a different variable, you have to remember that the chain rule is going on. Our inner function is this y variable. It's a function now because it's defined in terms of x. It isn't just y, like you're not taking the derivative with respect to y. So we need to take the derivative of y with respect to x, which we have a way of saying. We call that dy dx. And so there's your dy dx. These problems will almost always have a portion where now what you need to do is to solve for dy dx. And so in this case, the way you would do that, First step is you would subtract 2x from both sides. So you'd have 2y is equal to 2y dy dx is equal to negative 2x. And so you'd solve this out, divide both sides by 2y, you'd have dy dx is negative 2x over 2y. You would have the derivative of y with respect to x is negative x over y. So let's check a few of these to make sure that this makes sense. If we look at the point 0, 5, well, that should tell us that the derivative of y with respect to x, which is negative x over y, is negative 0 over 5 equals 0. So what that's telling us is we should have a horizontal tangent line when x equals 0 and y equals 5. And we do. We have a horizontal tangent line there. We have a slope equal to 0. So let's try a few more. 5, 0. If we go and we plug in 5, 0, dy dx is equal to negative 5 over 0. Well, that's undefined. So this is undefined. And so what we should have here is a vertical tangent. And we do. At 5, 0, we have a vertical tangent. We have an undefined slope. If we look through just two more, negative 3, 4. So we do the derivative of y with respect to x is equal to negative 3 over 4. So we're going to have a slope of 3/4. Let's just gut check that. At negative 3, 4, up 1, 2, 3 over 4. Yep, this looks like, if I can draw it, reasonably enough, that looks like what the slope of that tangent line would be. The only ones left is the one that I drew originally at 4, 3. dy dx now would be equal to negative 4 over 3. So let's check. If we go here, down 1, 2, 3, 4 over 3, yep, there is our tangent line slope. So the key here, right, this is something that is very tricky to understand the why. The why is that this is a chain rule problem because you are not taking the derivative of the same variable. You are taking the derivative of a different variable. And so we say, okay, let's pretend it's y of x squared. So we would have 2 times the inner function, 2 times y, times dy dx. Now, this is, I would say, one of those problems where you can very easily memorize the what to do. The why is quite a bit trickier. So as long as you're hanging with me on the what to do, the why will come eventually. So let's do a couple of examples of these. If we have y squared equals 2x plus 3y, and you are asked to find the derivative of y with respect to x, what we do, and I'm going to write this out every time like this, the derivative with respect to x of both sides. You want to get in the habit of writing this out every time. It's a serious partial credit point. And so we're taking the derivative again with respect to x. So we'd have 2y here times dy dx times the derivative of y with respect to x. This is just the chain rule happening because you're not taking the derivative of y with respect to y anymore. You're taking it with respect to x. Equals 2 plus 3 dy dx. Because we are not taking the derivative with respect to y, we are taking it with respect to x, so y becomes dy dx. The derivative of 2x with respect to x is just 2, but the derivative of 3y is 3 dy dx. It's like a placeholder. It's like, well, we don't know what the derivative of y with respect to x is yet. We are going to solve for it. And so this problem gets a little bit trickier in that now you have a few different dy dx's. So we need to get all of our dy dx's to one side. So what I'm going to do is, and you'll see why in a second, I'm just going to subtract 3 dy dx from both sides. What that's going to leave us with is 2y dy dx is equal to 2y dy dx minus 3 dy dx is equal to 2. And what this allows us to do is to factor out a dy dx. And the fact that we've factored it out allows us to then divide by 2y minus 3 on both sides so that we have dy dx equals 2 over 2y minus 3. And so what this basically says is, as long as you can tell me the y coordinate of this function, I can tell you what the slope of that tangent line is. It's 2 over 2y minus 3. Let's see, how are we doing on time here? We're at 11 minutes already, so I'm just going to skip straight to, we'll do those other ones in class. I'm going to skip straight to one more example here. Find the coordinates of the points where 4x squared plus y squared minus 8x plus 4y plus 4 equals 0 has a horizontal tangent. Well, a horizontal tangent is going to be when you have dy dx where the numerator of that function is 0. So I need to find what the slope of the tangent line is. If I want to know when it's horizontal, when the tangent line slope is horizontal, I need to know what the slope of the tangent line is. So I take the derivative with respect to x of both sides. So the derivative with respect to x of 4x squared plus y squared minus 8x plus 4y plus 4 equals 0. So the derivative with respect to x of 0 doesn't really matter. So what we'd have here is it's with respect to x, so 8x is fine, but plus 2y needs a dy dx. Minus 8x is fine, but plus 4y needs a plus 4 dy dx. And the derivative of 4 is 0. So we have all of this is equal to 0. We move the 8x and the minus 8 over to the other side, so we'll have 8 minus 8x, and we'll have that's equal to 2y dy dx plus 4 dy dx, 2y plus 4 dy dx is equal to 8 minus 8x. Finishing this off, we'd have dy dx is equal to 8 minus 8x over 2y plus 4. And so we could divide all 4 of those things by 2. So let's just simple this up. We'd have 4 minus 4x over y plus 2. Well, we're going to have a horizontal tangent line when the numerator is equal to 0. So that's going to be when 4 minus 4x is equal to 0, when 4 is equal to 4x, when x is equal to 1. Now the tricky part about this one, and we'll do a vertical tangent later in class, the tricky thing about this one is they didn't just ask me for the x, they asked me for the coordinates of the point. So this is a bit of a pain in the butt, but I need to go back to this original function, 4 times x squared plus y squared, and you'll see why I'm doing this in a second, minus 8 times x plus 4y plus 4 equals 0. That is a true statement in the original function, and I need to go ahead and plug in the 1 for x and solve for the possibilities for y. This will be 4 plus y squared minus 8 plus 4y plus 4 equals 0. Working this all out, the 4, and the negative 8 make 0. So we want to know, when does y squared plus 4y equal 0? Well, that's going to be y times y plus 4 equals 0. That means y equals 0 or negative 4. So our two solutions here would be 1 comma 0 and 1 comma negative 4. Those will be our two solutions here. That's an example of a difficult problem you could be asked to do with implicit differentiation.